Okay, so let's get on with the course. So last week it was guest lectures in these applied areas within ICT in general. So power engineering, process control, traffic safety, and e-health. So just let me remind you that these are not just for your own learning, but they're also an integral part of the course. So they will show up on quizzes and exams and so forth. But today we will continue our journey. So remember that last time we met physically, we talked about ARQ protocols. So we're going to finish that off today and then very briefly go through some other things which are not very difficult but still part of the course. And you will mostly have to read up on that yourself because we're running out of time a little bit. So I want to spend time on those things which are a little bit more, maybe more difficult. So today we will start on medium access control. So, but before we get started, I would like to advertise this event. So, as you know, it's time soon to select your master programs if you have not already done it. And the one that is most related to the stuff that I do research-wise is this MPCOM, Master Program in Communication Engineering. And so we have an event where the master programs at electrical engineering will be, what should we call it, advertised. And MPCOM will be part of this event on the 27th of February, 12 to 1 in HC3. And so it's free food if nothing else, right? So please show up. And we have two excellent external speakers here, Christina from Ericsson and Katrin Sjöberg from Volvo Group. So the Volvo, which is not Volvo Cars. So they do everything else, right? So trucks and buses and all these things. And talk a little bit about how communication relates to what they do and what they see the future needs for people with competence in these areas. Okay, so back to business. We talked about ARQ. So ARQ, the main thing is that we would like to deliver frames or we would like to deliver service data units over an unreliable network, and we would like to guarantee that we can deliver error-free service data units without duplications and in order. So that's the main idea. And there is like a generic recipe for doing that in the transmitter and receiver side. I won't go through this, you've seen it before already. And then there are different variations of this, and we talked about three main things: stop and wait, go back and selective repeat. And essentially they follow the same recipe with different window sizes. But the overall logic is very similar in between them. We will talk very briefly today that if we have bidirectional rings, that is, we have a sender and a transmitter where service data units goes this way, could also be very often that it goes the other way also. So we have two processes, two ARQ processes working in parallel, one from here to here and one from here to here. And then we can utilize that to do something called piggybacking, which essentially means that instead of sending specific acknowledgement frames, we put them into a data frame or information frame which is actually going anyways in the right direction. So we'll see that in a very short while here in more detail. Performance metrics of this is the effective rate, or performance metrics of ARQ is effective rate, and that's the data rate which is experienced by the layer above. So if I'm implementing ARQ protocol, I'm providing a communication service to the layer above me, and the data rate that the layer above me perceives is the effective rate. And the efficiency is then the ratio of the effective rate, so the data rate that the layer above me perceives, divided by the rate that I get from the layer below me. So that tells me the efficiency really is a number that tells me something about how efficient my protocol is to deliver as much data rate as possible up in the protocol stack. Stop and wait, effective rate and efficiency, you've seen these equations, so I would just briefly summarize them. But essentially, what we want, the effective rate is simply the number of upper layer bits that we can deliver divided by the time it takes to deliver them. Okay. So for stop and wait, we transmit an information frame of NF bits, including some overhead bits. So the number of information bits that we are actually transmitting, or the number of bits in the service data unit that we get from above, is just NF minus NO. And then we divide it through by the time it takes to deliver that, which is T0 seconds, or this time here. And this time is also it's known as the reaction time. It's also known as the turnaround time or round trip time. These are same things, right? And then, of course, if we have errors, then things degrade a little bit. So if PF is the frame error probability, then the effective rate and the efficiency goes down a little bit. So I won't go through the details here. For go back N, we did a derivation of that, and then we get this effective rate and this efficiency. And for selective repeat, we can do the same thing as go back N. We just plug in N equals 1 here, and then we get 2 new formulas here. So again, I won't go into the details here, but if one looks at these equations a little bit, we can draw the following rather important conclusions about which one to select. Okay, so which one should we select? Stop and wait, go back N, or selective repeat? Well, that depends. And what does it depend on? Well, stop and wait works very well as long as we have small delay bandwidth products. Okay, so then stop and wait is a good choice because it's simple, you know. If we have longer or where the delay bandwidth product is no longer small, then go back N is a better choice. However, only a better choice if the frame error rate is small, because if the frame error rate becomes large, then it's no better than stop and wait. One can simply see that from the equations. So when we then have not small delay bandwidth products and not small frame error rates, then we go for selective repeat. So selective repeat works well under those conditions. It's also the most complex protocol. Okay, so you know, one should always pick the simplest one if one can, but if it's not good enough, then we have to go for the more advanced solutions. Okay, a little bit of bidirectional links here. So in many cases, information flow goes from A to B and at the same time from B to A. That is very often the case. And then we can reduce the overhead in the protocol by embedding acknowledgements of these control frames into the information frames. So, for instance, okay, and this is called piggybacking. So an example here, we have node A and node B, and data flows this way. Okay, in the A to B service data units, it goes this way. But there is also B to A service data units that go the other way around. Okay, so if we forget about the lower part here and just concentrate on the upper part here, this could be any of your favorite ARQ protocols. In this case, it happens to be a go back N protocol. So then there is a state variable here for the transmitter and a state variable here for the receiver. For the ARQ protocol that goes from A to B, like this. And then there is also a parallel ARQ process with another state variable at the transmitter here and one at the receiver for the ARQ protocol that goes this way. Okay. So normally in an ARQ protocol, we send service data units in that direction from A to B, and then acknowledgement frames back from B to A. And what is in the acknowledgement frame? Well, it's the red state variable here. So what we do then is to take the state variable here and we plug that into the service data unit, which is actually going the other way. So it piggybacks on that transmission. Liftar, essentially, right? Because there is a frame going in that direction, so why not tag along, right? Then we can save on the overhead it takes to transmit a frame, because you have to add all the CRCs and whatnot, right? So, and the same thing goes, it's completely symmetrical in the other way, right? So the state variables for this receiver is piggybacked onto the service data units that go the other way around. Okay, so this is piggybacking. Questions? No? Okay. Maximum window size. So we have a window size at the transmitter and one at the receiver. For stop and wait, they're size 1, both of them. For go back N, the send window is larger than 1, but the receive window is just 1. For selective repeat, both of them are greater than 1. So we use sequence numbers to keep track of the send and transmit windows, and these are encoded into a certain number of bits. So typically we have then m bits, small m. So then the numbers we can have for the sequence numbers are from 0 to 2 to the power of m minus 1. And then if we have a certain window size, or actually m here will then determine how big the window size can be. Because this, we need a certain number of sequence numbers before we can start to reuse them. So we know for go back N, it's enough with just 2 sequence numbers, 0s and 1s. We just need a 1 bit for that. However, for go back N, we need more than that. So the send window, which is larger than 1, has to be less than 2 to the power of m minus 1. One can show this. So if we have 16 bits, it's 2 to the 15 minus 1, which probably is quite large window actually. The receive window would just it's equal to 1, so we don't need any. Has no real constraint on m here. For selective repeat, both the send window and the receive window has to be smaller than 2 to the power m minus 1. So if we have 16 bits, it's 2 to the 15 for the send window and 2 to the 15 for the receive window. Okay, so it's not so hard to show this, and there is a derivation of that in the book, so we won't spend time on that right now. Questions? No? Okay. Now we continue, and we're going to talk about 2 things here in very, very quickly. So I will actually ask you to read up on this on your own, and if you have any questions, just come and see me or Shoaib, and we'll explain how this works. It's not very difficult, but it has, you have to read it and understand it, of course. So flow control. So what is flow control? Flow control is used to avoid that a fast transmitter overwhelms a slow receiver. Okay, so this could be a slow receiver, while a fast transmitter could be, a YouTube server or something like that, which has enormous capacity, so it can easily overwhelm this by just pushing gigabits and gigabits per second into this device, and this device will simply not be able to handle that. So one has to pace, the transmitter sometimes has to slow down a little bit in order to match the capabilities of the receiving device, and that's called flow control. And so how do we do flow control? Well, there are 2 main ways to do that. One way is the device says, okay, I'm ready to receive, and then when it feels like, okay, it's getting too much, it's basically say stop, okay? And then process the data and then say, okay, I'm ready to receive again, and then stop. So this is called, sometimes called X off and X on. So simply that the receiver informs the transmitter about its availability to process data. One can do that in a slightly more refined way, and that is if we have these sliding window transmitters. That is, we have a transmitter which has a send window, and remember that the send window contains the data which is now currently under transmission. So if the send window is 5, what the transmitter can do then is can rapidly transmit 5 frames, service data units, and then it has to wait until these gets acknowledged. Okay, so the size of the window tells us a little bit on how quickly the transmitter can transmit. For a large window, the transmitter can transmit many frames in rapid succession. For a smaller window, it can only transmit a few, right? And that tells us a little bit about the data rate of the transmitter, because when the send window is full, the transmitter cannot send any more things until it gets an acknowledgement. So what the receiver can do is they can instruct the transmitter to adjust the send window size to fit the available buffer space at the receiver. Okay, so that's an indirect way of doing things here. Instead of having X on and X off, we simply use the acknowledgements, or we actually tell the transmitter, you know, please reduce your send window, or now you can increase it, or whatever. So this is a technique which is used in TCP, for instance, where the receiver tells the transmitter a little bit on what the send window, which would be preferable. Okay, so that everything I will talk about flow control, right? There are many details to this, so please read up on this in the book. Second thing, framing and bit stuffing. And framing has to do with that if a receiver sees a sequence of ones and zeros like this, it needs to know where one frame starts and one frame ends. Okay, so it could be hard if you just get a sequence of bits like this. Where does the next frame start or end? Well, maybe this is the frame delimiter here. Okay, so framing has to do with putting in special frame delimiters into a sequence of bits or bytes. And it has to do that in a way such that the frame delimiter cannot be mistaken for a valid sequence of bits. Okay. And remember that these are frame bits. They could be any sequence. We don't put any constraints on those, right? It could be any sequence of ones and zeros. So how can we put in a frame delimiter, which is also a sequence of ones and zeros, in order for this to be uniquely decodable at the receiver? Okay. And it turns out that it's actually not that difficult to do this, but it requires a little bit of thinking. And that thinking is covered well in the book, so you can read about that. And the process to do that is either to use byte stuffing or bit stuffing. Okay. So if you go through these two slides, you figure out how byte stuffing and bit stuffing works. Okay, so that's everything I'm going to say about framing, right? It's not rocket science, right? But you need to spend a few minutes on this, otherwise it will be difficult to do. There will be a problem at the exercises, and every now and then it pops up on the exam also. Okay, so let's go now to the main topic of today, which is multiple access communications. So remember what we have done up to now. We talked about the physical layer, how to implement a link from transmitter to receiver. We talked about how to use this link, which could have bit errors on it, in order to provide reliable transmission over this using ARQ protocols. Okay. Now we will talk about how to share this link between many transmitters. Okay. So the canonical case for this would be a Wi-Fi system, for instance. So we have an access point, there's a bunch of Wi-Fi devices here, we share the same radio channel. How can we do that? Okay. Another case would be an Ethernet or a classical Ethernet, where we have a cable which is shared by many transmitters. They need to coordinate their transmissions to avoid collisions. Okay. So medium access control is about sharing a medium in a way which is fair and also that we avoid using the medium inefficiently. And we use the medium inefficiently if transmissions sort of overlap and collide. Okay. So a very good thought model around this is that we are all sitting in this room. Now suppose that we put on, we turn off the light or put on ski masks or whatever, and then we can't see each other, and now we start to communicate. Okay, so how are we going to communicate with each other? Well, somehow we need to figure out when somebody needs to talk and somebody needs to listen, and so forth. So we need to coordinate this somehow, and that is the purpose of these medium access control protocols. Okay. So methods to share a medium, cable, radio channel, fiber, whatever, between several transmitters. And these transmitters are also known as nodes, users, or stations. I will use stations as we go along, because I think that is what's used in the book, and it's sort of like common in the medium access control literature to use that. So we have station number 1, 2, 3, and say that in this case we have 7 of those, and they share a common medium here, and they would like to transmit frames within this cloud, and the frames should not collide, or at least they could collide, but eventually we would like the frame to reach its destination. Okay. So approaches to this media sharing or medium sharing is, there are 2 main principles, and one is called static and one is called dynamic. So the static one, which is I guess somehow the oldest, well, I don't know. Anyways, static channelization, if we want to talk about that, what we do then is we partition the medium into channels, and there are various ways to do this. We will talk about that later in the course. But let's think of an example to illustrate this. For instance, regular broadcast radio, FM radio. We have then channels, right? You dial in the carrier frequency of the transmitter. So you have P1 here, P2 here, P3, and then all the commercial radio channels, like whatever they are called nowadays. That tells me which station I listen to, by the way. Anyways, so we allocate these channels on a very, very long time basis. Like the P1 transmitter in Gothenburg has been at the same carrier frequency for a very, very long time, and will probably be there for a long time in the future. Okay, so this is one way to share channels, right? So remember that if we were in the room here, we divide up the time to talk, or the frequency to talk, and we hand that out to the users, you guys, and including me, and then we stick to this for a long time. Dynamic, on the other way, is not to do this. We still use channels somehow, but we don't allocate them fixed to a user for a long time. Rather, we move them around between the users or the stations or the nodes, same thing. So we move them around the stations where the need is. So if Shoaib has a lot of data to transmit, we give him a lot of channels, right? But then when he's done, we reallocate those channels to somebody else. Okay, so that's dynamic. And here there are 2 main things to do this. Either we do it in a scheduling way or random access way. Scheduling is like a careful planning of this. We will look at a few techniques next time we meet. Polling is one of those things. So we reserve resources for users in a careful way. An example of this is something called a token ring. I don't know if you heard of that, but we'll see one a little bit later in the course. The other one is called random access, or maybe uncoordinated access or unscheduled access. And this is what we will talk about today. And this is a very loose coordination between the users. So it's fast, it's not very complicated, but it's also not super reliable. Okay. So a standard technique to do this is that we listen to the medium, and then if the medium is free, then we transmit, and then we wait for an acknowledgement, and we retry if necessary. So it's like almost like if you go to a cocktail party or whatever, you just talk, right? And sometimes the person that you talk to hears what you want to say, and sometimes not. And if he or she does not hear what you say, they could be polite and ask you what you wanted to say, right? And then you retry. When it's more scheduled, think of this as in the Swedish parliament, right? There's a speaker that hands out the rights to each and other politicians to say their thing, and nobody else can talk during that time. So that's the more scheduled approach. Okay, and examples for this is Aloha, Ethernet, a few other things. Wi-Fi to some extent is also in this domain. 3G, 4G, 5G is more in this domain. Okay, questions before we proceed? No? Okay, so how many medium access control protocols are there, and how should we choose among them? And the answer to the first one is there is a bunch of them. There are many, many, many. And which one should you choose then? Well, it depends. So what does it depend on? Well, it depends on what you would try to achieve. So first of all, what are we talking about when we're talking about protocols here? We're talking about the MAC layer, medium access control layer. And if you remember, the physical layer is one which is closest to the medium. So the MAC layer is just above it. So sometimes it's a standalone layer, or sometimes we say it's a sub-layer of the data link layer. So we can think of the MAC layer as the lower part of the data link layer, if you like. So considerations when choosing a MAC method is, first of all, what type of data traffic do we need to handle? So there is some data coming down here. Okay, what type of data is it? Is it a regular stream of bits with a fixed rate? Or is it sometimes high rate, sometimes low rate? What is it? Okay, so if it's steady or bursty, that makes a big difference. If it's short or long messages, that makes a big difference also to what makes an efficient MAC protocol. Something which is of interest, for instance, if you looked at the vehicular traffic safety lecture last week, you know that the delay over the channel is quite important here. So here, the transfer delay is quite important. Is it important or not? It depends, right? And if it's important, then we need a MAC layer to support that. Okay, because different MAC layers could have different delays associated with them. Fairness is something also which is important. So what is fairness? Well, fairness is essentially that all the nodes, all the stations which are sharing the medium, get a chance to use it on some type of fairness criterion, right? Scalability, and that has to do with how many stations we can handle at the same time. So for some MAC protocols, there might be, it works well when there are relatively few nodes sharing the medium, but it doesn't really work well when there are thousands, maybe. Okay, so scalability is also important. Okay, and then of course we always want to have good efficiency. So the efficiency, we will see later on what that means, but it essentially means that the MAC layer should use the resources of the physical layer in a good way. So to provide, don't waste the resources here. And then sometimes other quality of service, also QoS here stands for quality of service. And these could, this could be, for instance, it could be this delays and the jitter with the associated with this delay. But it could also be other things. For instance, that one simply has a guarantee that this that you're able to transmit data whenever you want to do that. There could also be priorities which are important. For instance, there are some messages that might be more important than other things. Okay. And then, of course, our cost is also important, and reliability. So, questions so far? I mean, this is, you know, very high level and fluffy and so forth. So let's go down to business and see what we can do here. What we want to do is, first of all, to nail down a few performance metrics. So how can we say whether a MAC scheme is good or bad? So if we look here at the right-hand side of the slide, we have two nodes. I haven't drawn the upper layers here, but it has a MAC layer and a physical layer. And here we have another node, another station with a MAC and physical layer, and they're attached to a common medium here. Just for an example, I've just drawn this as, you know, a cable that's shared. It could be a radio channel also, if you like. And this radio channel here has some capacity, and we measure that in its ability to transmit bits per second. So this is the R here, the parameter r, is the data rate of the medium. Okay? And that depends, of course, on how the physical layer is designed. But let's say that the physical layer is designed and it's fixed, it doesn't change. It's just being able to support r bits per second. So this is the medium data rate, or sometimes we call that the capacity. Okay, so the transfer delay is the first parameter that we care about, and that's also known as the Mac-to-Mac delay, T, capital T here. So what is that? Well, it's the time it takes from one frame to pop down into the Mac layer here until it pops up at the appropriate Mac layer, okay, which whatever Mac layer that is. It could be many, it should be in the right node, right, to the right destination. So the time it takes to go from here, entry point here, until it goes up here. We measure that time, and we call that capital T. That's the frame transfer delay. Okay, and here one can measure this frame transfer delay at various places in the protocol stack, but since we are dealing with the Mac layer here, we are looking at this interface. That is the interface between the Mac layers and the upper layers, both at the transmitter and at the receiver. Questions about that? No, it's clear? Okay. So typically this transfer delay is a random variable because it sometimes it goes fast, sometimes it goes slow. It depends on what's going on onto the channel, obviously, right? Sometimes there is busy here, sometimes not, and it depends on how the protocol resolves this. So typically T here is a random variable, and we then quantify that, say with its average or its CDF or something like that. Okay. Throughput is another thing. So what is throughput? Well, here's actually a little bit of confusion, I would say, in the literature and so forth. So just because somebody says throughput, it's not clear what he or she means by that. Okay, so what I mean with throughput, at least at the moment, at this point in the class, is throughput is the actual transfer rate through the shared medium. Okay, so either in frames per second or bits per second. And this is typically less than the medium capacity. Okay, so throughput has to do with how long it takes to transmit this frame to here, which takes t seconds. So there are a number of bits popping down here, number of bits popping down here, bits per second, and they all share this r. And if one looks at the, we will see this in more detail as we go along, but the throughput has to do with the useful data rate over these channels. And not only between these two, but all the channels, all the pairs of transmitter and receivers which are sharing the medium at the same time. Okay, so suppose, for instance, that we have M users. So we have M stations, and they share this physical layer, this physical medium here. Then suppose that they together generate lambda frames per second, and each of these frames have L bits. Okay, then the normalized load is defined as follows: lambda times L. Okay, and this is the total bit rate which is offered to the medium, and then we divide through by the capacity of the medium. Okay, so let's maybe do a small example on this to illustrate what is the meaning of this parameter. Yeah. So we have a number of stations. Let's call it station number 1. We have station number 2. And keep on going, and we have station M, say. And these are all attached to a physical medium like this. Like Okay. So what do we know about the medium? Well, the medium has a certain inherent capability of transmitting bits. So the data rate on the medium is r bit per second. Okay. And this capacity then needs to be shared among all the users of that medium. Right? So this r bits, the r bits that we have to our that is provided to us through the medium needs to be then shared among all of these stations. So the r bits, we can hand them all to station number 1, for instance, or r half to station 1 and r half to station 2, but then nobody else can transmit. Or we can move r bits per second to station number 1 until station number 1 is happy, then move over to station 2 and give it r bits per second for time, and so forth, and go around. There are many ways we can do this, right? But somehow these r bits needs to be shared. The r bits per second needs to be shared. So the meaning of the variables that we saw on the slide here is we can define them as follows. So lambda n, we can think of that as the number of frames per second which are generated by station n. Okay. So station number 2, for instance, here would generate lambda 2 frames per second on the average, right? Station number 1 would have lambda 1, station number m would have lambda capital M. Then lambda is the sum of all these lambdas, okay? So it's the sum of frames, number of frames per second generated by all stations. And obviously this is the sum of all the frames, all the lambdas. Okay. Now, it's not sure that the system will be able to handle this load. Okay. It could be like, for instance, that we have some type of malfunction here, or there is something going on that makes this being too big of a demand, right? It's not necessarily true that that all these frames could be sustained by these r bits per second here. But nevertheless, we can think of this lambda here as the traffic which is offered to the medium, not necessarily which is supported. So it could be in an overload situation, but it could also be an underload situation. But how many bits per second are we talking about here? Well, we have lambda frames per second in general, and then we multiply that with L, which is the number of bits per frame. Then we get the number of bits per second. So lambda times L here is the total bits per second generated by all stations. And L here is the number of bits per frame. Okay. If you remember, in the ARQ chapter, it was called NF. It's the same concept, but a different symbol. Okay. Now, during stable situations, where the offered traffic is low enough for the medium to handle it, then the throughput let's call it RU, is equal to the offered traffic. Okay. So this is the desirable situation where the stations are generating frames at the rate individually so that collectively they are not overwhelming the medium. Okay. So in stable situations, and we still haven't guaranteed that this is the situation, but if it is, then the throughput is equal to lambda L. In an unstable situation or an overloaded situation, lambda L is greater than what the medium can support, and then the throughput is much less than the offered traffic. Okay. So we can define something called the load, and the load is this rho, and it's the ratio between the offered traffic, which is lambda times L, divided by the capacity of the medium, which is R. Okay. And this is okay. So this number here could be larger than 1 if we're in an overloaded situation. So what does it mean when it's greater than 1? It means that the offered traffic is actually more than what the medium can handle. Okay? And in that case, the throughput will not be equal to lambda L because it's impossible. We cannot push more bits per second through the medium here than R. R is the absolute maximum, right? But if we have a lower lambda, lambda times L actually, when the load is less than R, we're in a situation where it's at least theoretically possible to do this. Okay. For each medium access control, okay, so for a specific MAC, there is a max supported load. Which is rho max, okay, and that it has to be less than 1. Okay, typically it's rather, depending on the situation, how, and we will see what that means a little bit later, depending on how hard it is to coordinate these nodes, this could be significantly less than 1, but for sure it can never be more than 1, because if it's more than 1, it means that we push more bits per second through this medium than R, which is impossible. Okay, so the supported load is always less than 1. For a MAC layer, there is an upper supported upper limit on the load, and it's called rho max. And it's different from different medium access control layers. Obviously, we would like rho max to be closer to 1, because that means we use the medium efficiently. Questions? Okay. And then just a final thing here. The throughput then is equal to lambda L, but only if lambda L is less than, only if lambda L divided by R is less than rho max. Because if it is, then the MAC can support it. If it's above rho max, it's not supportable. Okay? Okay, so let's take 15 minutes.